In this video, I'll discuss an idea of optimization. Here are the main points we've addressed in the video. We can tell whether a function has maximum and minimum values by finding critical points of its derivative. Critical points are where the derivative of the function is 0 or undefined. When a derivative of a function switches from positive to negative values, the function has a local maximum. When a derivative of a function switches from negative to positive values, the function has a local minimum. To identify global maxima and minima, we also need to look at the endpoints of the function. So, optimization is about finding the largest and smallest values of a function on an interval. When many people buy a car, they think about its fuel economy, how far it will go on a gallon of gas. One thing that many people don't realize is that your fuel economy is affected by the speed at which you drive. So in this video, we examine the relationship between fuel economy and speed and try to find the speeds that will give you the best and worst fuel economy. According to National Laboratory data, it has developed a system to simulate a mid-sized car driving at highway speeds and predict the fuel economy. So for example, they found that when the simulated cars were moving at speed of 50 miles per hour, they had a fuel economy of 40 miles per gallon on average. In this table, we can see that what the largest and the smallest value of fuel economy are. But the table only gives us the data at specific speeds. And it is possible that cars might have a higher or lower fuel economy at speeds that are between those displayed in the table. To get a better sense of the patterns in our data, let's look at a graph. This graph shows data points in the table. To get a better sense of the pattern in the data, we can add a trend line. And we can also find a formula for this trend line. This shows the equation for the function of f of s, fuel economy as a function of speed, measuring fuel economy in miles per gallon. Let's temporarily remove the data points from the graph and just look at the graph of the function. So our goal is to find where the fuel economy is the largest and smallest. The largest value will occur somewhere around here when the graph hits the peak. This happens when f of s stops increasing and starts decreasing. Let's take a quick detour to remember something important about derivatives. It will be important to think about how functions relate to its derivative. You probably remember that when a function is increasing for a particular x values, its derivative has a positive y values. When a function is decreasing for a particular x values, its derivative has negative y values. When a function is constant or for a particular x values, its derivative has 0 y values. And if a function has a cusp or a jump or something strange happening for a particular x value, then derivative is not defined. So keeping in this mind, let's return to the graph of fuel economy versus speed. We know that fuel economy will be largest at a speed where f of s stops increasing and starts decreasing. And in calculus terms, this is when f prime of s switches from positive values to negative values. To figure out where this happens, let's compute the formula for the derivative function. F of s is a polynomial function, so we can use the power rule here to get f prime of s equals 0.00008 s to the third power minus 0.007 s squared plus 0.438 s minus 4.035. And this is measured in miles per gallon per miles per hour. Let's look at the graph of f prime of s, the derivative graph. Here's the graph of f prime of s. Here are some values of s where f prime of s is positive. So when the graph, so when the car is traveling at any of these speeds, each additional mile per hour will increase the fuel economy. And here are some values of s where f prime of s is negative. So when the car is traveling at any of these speeds, each additional mile per hour will decrease the fuel economy. And so when we switch from increasing to decreasing fuel economy, this is when we'll find the maximum fuel economy. In this case, this happens when the value of f prime of s is 0. When f prime of s equals 0, the value of s is called a critical point. To find the value of this critical point, we will need to set f prime equals to 0 and so for s, either using quadratic formula or computer. We will get s equals 50.252 miles per hour. So for these simulated cars, the fuel economy is maximized when traveling at a speed of 50.252 miles per hour. We can mark this s value and see this on the original graph. Here's the graph of the fuel economy versus speed, the original graph. And we can see that it hits its maximum value when the speed is 50.252 miles per hour. Now, what about finding the minimum fuel economy? The minimum fuel economy should occur when f of s stops decreasing and starts increasing, or in calculus term, when f prime of s switches from negative values to positive values. However, in this scenario, there isn't any speed where fuel economy stops decreasing and starts increasing. Instead, we can see that fuel economy is lowest at either smallest speed value we're using or the largest speed value we're using. These are called endpoints of the interval of speed we're looking at. To determine which of these speed values gives us the smallest fuel economy, we can either look back at the data in our table or use the formula to compute the fuel economy values at each of these speeds. For 45 miles per hour, the data gives us 43 miles per gallon. And at 75 miles per hour, the data gives us 32 miles per gallon. Thus, we'll have a minimum fuel economy when we're driving at 75 miles per hour. So to summarize all our work, optimization is when you want to find maximum and minimum values of a function. The maximum value will occur when values of derivative go from positive to negative. And you also might need to check the endpoints of the domain. Similarly, the minimum value will occur when the values of derivative go from negative to positive. And you might also need to check the endpoints of the domain. The places where derivatives switch between negative and positive are examples of critical points. These are places where the values of derivative is 0 or potentially undefined. So, to find all the potential points where a function has a maximum or minimum value, you would identify all the critical points and endpoints, then see which of these maximum values and which are minimum values. So let's look at another example. Just like the first example, we use the example fuel economy as a function of speed. In the previous example, we looked at a data that was produced by a computer simulation. In this video, we look at data that was collected in 1997 by Oak Ridge National Laboratory, which actually drove a bunch of cars around and tested the track at various speeds and recorded their fuel economy. As before, to get a better sense of pattern in our data, let's look at a graph. This graph shows the data points in the table. To get a better sense of this pattern of data, we can add a trend line. And we can also find a formula for this trend line. This shows for equation function f of s, fuel economy as a function of speed, measuring fuel economy in miles per gallon. As we saw in the previous example, our method is to find the critical points of f of s, that is, points where the derivative is either 0 or undefined. So first, we can use the power rule to compute the derivative of function of f of s. Next, let's look at the graph of this derivative function. Here is the graph of f prime of s, the derivative graph. Here are values of s which values f prime of s are positive. So if you are traveling at one of these speeds, each additional mile per hour will increase the fuel economy. Here are the values of s which values f prime of s are negative. So if you're traveling at one of these speeds, each additional mile per hour will decrease the fuel economy. And when the values of f prime s are 0, these are the critical points. Next, we need to figure out whether each critical point corresponds to the maximum or minimum value of the function. When the fuel economy switches from increasing to decreasing, the fuel economy is hitting a maximum value. That also happens right here. Similarly, when the fuel economy switches from decreasing to increasing, the fuel economy is hitting the minimum value. To find the actual values of critical points, we need to use a formula to plug the values in. We set f prime of s equal to 0 and get that 32.898 miles per hour and 54.214 miles per hour gives us maximum fuel economy. And 38.814 miles per hour gives us minimum fuel economy. Let's take a look at these points on the original graph of fuel economy versus speed. Here's a graph of fuel economy versus speed, the original graph. And we can see that a speed of 32.898 miles per hour gives us the local maximum. It's the largest value of fuel economy for a small range of speeds. But only a speed of 54.214 miles per hour gives us the global maximum, the largest overall fuel economy over the entire domain. We can see this in the graph because the global maximum occurs where the graph of fuel economy achieves its largest y value, the peak value, the most peak value. Similarly, a speed of 38.814 gives us a local minimum, its smallest value for a fuel economy for a small range of speeds. But just looking at the critical points doesn't tell us the global minimum. We have to also look at the endpoints of the function of the domain by finding the point on the graph with the smallest y value. We can see that the left endpoint will give us the global minimum. To wrap this up, we need to actually compute and report the actual fuel economy values for global minimum and maximum. We can plug the speed of 50 miles per hour into our formula to get the minimum fuel economy of 24.4 miles per gallon. And the maximum fuel economy is 32.305 miles per gallon.